So let's talk about the greatest common denominator problem, right? The greatest common denominator or greatest common divider or greatest common factor is saying basically given two numbers like 60 and 15. Oh, let's go with let's see, 60 and 15, right? What is the biggest number that divides both evenly? And in this case, it's 15 because 60 is divisible by 15 and 15 is divisible by 15, right? They're both cleanly and evenly divisible, right? Similarly, let's go with 6 and 80. The greatest common divisor there is 2 because 2 is the biggest thing that divides both 6 and 80. It's the biggest thing that divides both, right? So how do you calculate that? Well, just a couple more examples here. The greatest common divisor of 20 and 15 is 5. Biggest number divides both. 36 and 24 is 12. Right? These numbers, the biggest thing that divides them both, 38 and 18, is 2. And for 17 and 97, since I believe they're both prime numbers, right? Meaning that of course they're relatively prime to each other, meaning that they neither divides the other. The biggest factor they have in common is 1. So the greatest common divisor for the recursive algorithm there's this recursive algorithm, Euler's algorithm, very old algorithm that says given two positive integers m and n, that if n is a divisor of m, then the divisor then n is the integer that divides both. Otherwise, the GCD of m and n is the GCD of n m mod n. Now, I really hate mathematicians for this, okay? Because, like, this aggravates me to no end, right? First off, and it's just because of one thing. They chose the variable names to be m and n. So first off, not only does it sound like I am talking about candy all the time, which is making me hungry, okay? It also, m and n just sound so similar. It's a terrible thing, right? But fortunately, we're computer scientists, so we don't have to deal with this rubbish, okay? So let me go ahead and rewrite the algorithm for you guys over here, and then we're going to apply it to these things, because m and n is stupid, right? You guys can read more than one letter at a time. Okay, so given the GCD, to calculate the GCD, the greatest common factor of two numbers, we'll denote one to be the bigger and one to be the smaller, right? Instead of m and n, we'll do the bigger and the smaller. All right, if the bigger is divisible by the smaller, right? If the bigger one is divisible by the smaller, like in our case over here, 60 and 15, right? The bigger one is divisible by the smaller one. Then we found our greatest common divisor. GCD is smaller. Right? Makes sense, right? If this divides this, then congratulations, you are done. The other, well, if they don't divide each other, right, then what it says is that the GCD of the bigger and the smaller is the same as the GCD of the smaller and the, let's see, I believe it was bigger mod smaller. Just want to make sure. Yep, bigger, smaller, and bigger number. It wouldn't make sense otherwise. Mod smaller. All right. So let's go ahead and just see that this works, right? And I'm going to go ahead and grab the numbers that they use as the example here, right? Just to show you that this algorithm works. It's kind of really elegant, but it's incomprehensible unless I write it out like this. Okay? Now at least we can understand the directions, even though we have no idea why this works. Okay? But that's fine. So the bigger. So it's 20 and 15, right? What is the, so this is our bigger, this is our smaller. I'll always put the bigger on the left. So is the bigger divisible by the smaller? No, it is not, right? 15 does not divide 20 cleanly, okay? So what we have to do now is calculate 15 or 20 mod 15. We got to mod these two guys together. 20 mod 15, that gives you So 20 divided by 15, that gives you remainder 5. So now we say we calculate the GCD of the smaller and the big mod the smaller. So we calculate now the GCD of 15 and 5. So does this cleanly divide this? Yes, we're done. So the GCD is the greatest common denominator is 5. And right, if you check that, that makes sense. All right, what about 36 and 24? 36 and 24, right? Does 24 divide 36? No, it does not. Okay, so now we have to calculate 36 mod 24. That gives us 12, right? Everybody understand the steps? 30. So they don't. This doesn't cleanly divide this. So we have to mod these two guys together, right? Which yields 12. So now calculate the GCD of the smaller and the bigger mod the smaller. So 24 is the smaller, and the bigger mod smaller was 12. So 24 mod 12. Sorry, 24 is divisible by 12. So hurrah, we are done with that example too. What about 38 and 18, right? 38 and 18, right? 18 does not divide 38 cleanly, so we have to mod them by each other. So what the heck is 18 mod, what the heck is 38 mod 18? Well, we can just use subtraction. So subtract 18 to get from 38 to get 20, and that's still bigger than 18, so subtract again to get 2. Check on your calculators. 38 mod 18 is 2, right? And that also makes sense if you work the other way. 18 times 1 is 18. 18 times 2 is 36. That's as close as we can get to 38 without going over. So and then the difference there is 2. So now 18 and 2, right? So now, so is 18 divisible by 2? Yes, it is. So we're done. All right. Now for the last one, it was 17 and 97. So I'm going to go ahead and again put 97 over here and 17 over here, right? These do not evenly divide each other, not by a long shot. So I'm going to go ahead and just use my handy-dandy calculator instead of trying to compute this by hand, right? It could do modular arithmetic, but I just want to show you 97 minus 17. 18, that's 80, that's still bigger than 17, right, to do modular arithmetic. So minus 17. So let's see, 97, so 80 minus 17, still 63 minus 17, minus 17, minus 17. So we're going to end up with 12. So 97 mod 17 is 12. So now, is 17 cleanly divisible by 12? No, it is not. So 17 mod 12, that would be 5. What about 12 and 5? Is 12 cleanly divisible by 5? No, it is not. So 12 mod 5 is 2. Is 5 cleanly divisible by 2? No, it is not. So 5 mod 2 is 1. Okay, 2 and 1. Does 1 cleanly divide 2? I sure hope it does, otherwise everything about math I know is wrong. So the greatest common denominator is 1. So this algorithm works. It's a very elegant algorithm, right? And the way this is going to work is so now let's go ahead and code this up. Okay, so and this one is a bit different because it's recursive, yes, but we're not like subtracting 1, which is what we were doing for pretty much all the other ones. In this problem, we are doing public static int GCD of int bigger int smaller. right? As I was saying, we're not doing subtraction here, we're doing modulo, so we just need to think about how that's going to assure that we do. But let's think about our base case. What was the easiest case that we had, right? And that was if the bigger is divisible by the smaller, and that's fairly straightforward to check. We can pretty much see it if we know our numbers. So if 15, not 15, but if bigger mod smaller is equal to 0, return smaller, right? If there's no remainder after we divide bigger by smaller, right? That's what that means. Then smaller cleanly divides bigger. So voila. Otherwise, we need to return the greatest common denominator of the smaller and bigger number mod the smaller number. Now, I'm not quite done with this, but although this is the algorithm I wrote, right? But let's just think about this, right? If they're cleanly divisible, we're going to go ahead and just return the smaller numbers. So if we hit our base case, we're done. Otherwise, well, we take our smaller and put it in the right-hand side. And then on the left side, we put bigger mod smaller. Now, for now, just assume that bigger is always going to be bigger than smaller. Now, any number that is bigger than that's bigger than a smaller number, if it's mod by the smaller number, so if we're in a situation like this, then of course we're going to end up with a smaller number, with an even smaller number. This is going to be smaller than bigger or smaller. It's going to get closer to 1, so to speak. It's going to get it's going to get closer to 1, right? Now, why 1? Why is that important? Why will this get closer to 1? Well, eventually, if they aren't related, right, if these numbers are relatively prime to each other, like in this case, eventually what's going to happen is that there's going to be nothing else, that eventually bigger mod smaller will result in 1, like we did in this case. 5 mod 2 will result in 1, right? And once 1 is the smaller, variable, well, anything mod 1 will result in 0, so we'll return smaller. So it's always going to make progress towards our base case. Now, I was mentioning, though, this relies on the assumption that that the bigger number is actually bigger than the smaller. So if bigger is smaller than our smaller number, then we'll just swap them, kind of like we did for the previous problem. GCD smaller should be here on the bigger side, and the bigger should be on the smaller side. Right? Makes sense? Okay, so now to test it out, GCD 60, 15, okay, 2 and 15, that should result in 1, okay, and 15, and let's see, trying to think of something else divisible by 3, 66 and 15, there we go. So this works. So that's a pretty exciting function. So now, why are we using let's see. So we'll go into, so now on Monday I plan on going over another mathematical problem. There's typically another mathematical problem here that I go over, which is the Fibonacci case. We're going to leave that for Monday because it's pretty exciting what happens with that one. But for right now, next video, we'll go over the what is the value of using recursion versus iteration.